Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The conferral of the 19091 AM Turing Award upon Vinton, Cerf and Robert Kahn served as the definitive academic consecration of a revolution that had begun nearly 2 decades earlier. This highest honor, in computer science, was a formal acknowledgement of a reality already emergent. The world was being rebuilt upon the intellectual foundations laid out in their 1974 paper, A Protocol for Packet Network Intercommunication. This document, published in the IEEE Transactions on Communications, stands as a masterwork of systems design, a technical specification that doubles as a political treatise on the nature of open communication. It accomplished a task of immense conceptual difficulty, proposing a method for disparate, autonomous, and technologically diverse computer networks to communicate as a unified whole. The paper's enduring power emanates from its core architectural philosophy. It championed the layered abstraction and a principle of minimalist network-level requirements, pushing intelligence to the periphery of the system. This approach unleashed a torrent of permissionless innovation, creating the fertile ground upon which the modern Internet would later blossom. The true genius of Cerf and Kahn's work lies in its profound foresight, its elegant simplicity, and its implicit argument for a decentralized, resilient, and universally accessible fabric for human knowledge and interaction. To appreciate the radical nature of their proposal, one must first survey the fragmented digital landscape of the early 1970s. The world of networking was a collection of isolated archipelagos. The most prominent of these was the Advanced Research Projects Agency Network, or ARPANET, a landmark achievement in its own right, yet one whose native tongue, the Network Control Program, or NCP, was profoundly parochial. NCP was designed for a relatively homogeneous environment of specific host computers, creating a tightly coupled, connection-oriented system where the network itself bore significant responsibility for maintaining communication sessions. Beyond ARPANET, other experiments in packet switching were underway, each a testament to creative engineering and each speaking its own unique dialect. The Packet Radio Network, PRNet, explored the challenges of mobile, wireless data, while the Atlantic Packet Satellite Network, SATNet, grappled with the high latency and error characteristics of satellite links. A crucial intellectual wellspring existed across the Atlantic in the form of the French Cyclades network, championed by Louis Pouzin. Pouzin's design, in a departure from ARPANET philosophy, prioritized a simpler network layer that moved datagrams without establishing a connection. Responsibility for reliability was placed squarely on the host computers. This host-centric model, which Cerf and Kahn would later explicitly credit, provided a vital clue for solving the grander problem of intercommunication. The central challenge, therefore, was one of translation and federation. How could a message originating on a terrestrial, wire-based network like ARPANET traverse a high-latency satellite link and arrive on a noisy radio network, all without requiring each network to undergo a fundamental and costly redesign? The prevailing solutions were akin to building a dedicated translator for every pair of languages. Cerf and Kahn sought to invent a universal metalanguage, a kind of digital Ispra. The 1974 paper presented this metalanguage through a design of extraordinary elegance and conceptual power. The architecture rested upon 2 foundational pillars, the gateway and the transmission control program. The gateway, a conceptual predecessor to the modern router, was envisioned as a simple, stateless device sitting at the boundary between 2 different networks. Its function was purely mechanical. It would receive a packet, or what the paper termed a datagram, examine its destination address, and forward it toward the next appropriate gateway on another network. The gateway itself would retain no memory of the conversations passing through it. This statelessness was a profound design choice. It ensured that the internetwork's core would be simple, fast, and robust. The failure of a single gateway would affect only the packets currently in transit through it. Subsequent packets could be rerouted dynamically without disrupting the intoned communication session. All the sophisticated logic of ensuring reliable delivery was deliberately pushed outward to the communicating host computers. This hostile responsibility was to be managed by the Transmission Control Program, or TCP. In its original 1974 formulation, TCP was a monolithic protocol task with a wide range of duties. It would take a stream of data from an application, fragment it into a series of finite-sized datagrams, and affix a header to each one. This header was the heart of the system, containing the globally unique source and destination addresses that would guide the datagrams across the entire internetwork, from ARPANET to SATNet and beyond. TCP was also responsible for the complex choreography of reliability. It would manage sequence numbers to ensure that packets could be reassembled in the correct order at their destination, even if they arrived out of sequence after taking different paths. To the network, it would use checksums for error detection, allowing the receiving host to identify and discard corrupted packets through a mechanism of acknowledgements and retransmissions. It guaranteed that lost packets would be resent until they arrived safely. Furthermore, it incorporated rudimentary flow control, enabling a receiving host to signal to a sender that it should slow its transmission rate to avoid being overwhelmed. The paper's most revolutionary insight was to define the internetwork layer as a best-effort datagram delivery system. The network promised nothing about reliability, order, or congestion. This seemingly cavalier attitude toward data integrity was, in fact, the key to its universality. By making minimal assumptions about the underlying transmission medium, Cerf and Kahn ensured that any network capable of moving a packet from point A to point B could participate. The protocol offered a level of abstraction that liberated application developers from the specific physics of the wires, airwaves, or satellite links carrying their data. The conceptual blueprint laid out in 1974 underwent a crucial and brilliant evolution. As developers began to implement and experiment with the protocol, it became clear that the monolithic design of TCP was suboptimal. It combined two distinct functions: the end-to-end management of a reliable data stream and the hop-by-hop addressing and routing of individual packets. A pivotal 1978 memorandum, authored by Cerf, John Postal and Danny Cohen, proposed splitting TCP into two separate, layered protocols. The Transmission Control Protocol would retain its role as the high-level guarantor of reliable, connection-oriented communication. A new, leaner protocol, the Internet Protocol or IP, would take over the fundamental task of addressing and forwarding datagrams. This division was a stroke of modular genius. It created a clean separation of concerns and established the no-iconic layered model of the Internet. The IP layer became the narrow waist of the architecture, a universal substrate over which a variety of transport protocols could operate. This allowed for the creation of alternatives to TCP, such as the User Datagram Protocol or UDP, which offered a lightweight, connectionless service for applications like voice and video streaming where speed was more critical than perfect reliability. This refined TCP/IP suite became the subject of intense implementation and testing within the ARPA community. The process culminated on January 1, 1983, a date known as Flag Day, when the entire ARPANET switched its core protocols from NCP to TCP/IP. This was an audacious and meticulously coordinated migration that cemented TCP/IP as the de facto standard for the research community and pave the way for its eventual global adoption. The reception and triumph of TCP/IP were by no means a foregone conclusion. Throughout the late 1970s and 1980s, it faced a formidable rival in the form of the Open Systems Interconnection, or OSI, model, championed by powerful international standards organizations and telecommunications incumbents. OSI was a product of extensive committee-driven design. It was a comprehensive, several-layer architecture that specified everything with exacting detail. To its proponents, OSI was the formally correct, top-down, and professionally engineered solution. From this perspective, TCP/IP appeared to be a somewhat rough-hewn and pragmatic creation of a small group of researchers, an ad hoc solution that lacked the theoretical purity of the OSI stack. There is a certain historical irony in the outcome of this contest. While committees meticulously debated the finer points of the OSI protocols, the TCP/IP suite was already being deployed, tested and improved in a rapid, iterative cycle driven by a community of engaged users. It possessed the singular virtue of working and being freely available. The ultimate victory of TCP/IP was a victory for a different mode of innovation, a bottom-up, emergent process over a top-down, prescriptive one. The legacy of Cerf and Kahn's caper is thus inextricably linked to this philosophy of open, implementation-driven standards. This very architecture provided the stable, universal platform upon which subsequent innovators could build. A prime example is Tim Berners-Lee, whose creation of the World Wide Web in the early 1990s was predicated entirely on the existence of a globally interconnected network. The Hypertext Transfer Protocol, or HTTP, the language of the web, runs directly atop TCP/IP without the foundational connectivity that Cerf and Kahn's protocol provided. The web as we know it would be inconceivable. In retrospect, the 1991 Turing Award was a recognition that a protocol for packet network intercommunication was more than a mere technical specification. It was the charter for a new kind of public square, an architectural constitution for a global digital commons. Its core principless-led abstraction, stateless network cores, and the intent arguments have scaled with breathtaking success, accommodating a planetary network of billions of devices that its creators could scarcely have envisioned. The design's profound insight was to trust the endpoints of the network and to distrust complexity in its core. This created a dumb network that enabled the proliferation of smart applications, fostering an environment of permissionless innovation that has defined the digital age. The paper's deceptively simple proposal for moving packets between networks contained the genetic code for a system of unprecedented scale, resilience, and generative power. Cerf and Kahn's work stands as a paramount example of how a single, elegant engineering abstraction can reshape society, demonstrating that the most robust and vibrant systems are often those built upon a foundation of deliberate and principled simplicity. Its legacy is written in every email sent, every web page loaded, and every digital connection made across the globe, a silent, ubiquitous testament to the power of an idea that taught the world's computers how to speak a common language.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.